Hello, I wanted to talk to you guys about how to calculate this delta H knot of a reaction two different ways, but I want to split this up into two videos. So for this video, I'm only going to be talking about Hess's Law. I'm going to switch to blue so it makes it a little bit easier. So there are two ways to calculate this delta H knot of a reaction. Okay, so remember before this delta H, the delta sign right here means change, and H is enthalpy. So this is the change in enthalpy. Okay, so change in enthalpy, and this enthalpy encompasses all of the energy. So in a reaction, delta H will show you all of the energy that takes place from when you calculate from the reactants to the products. This little knot symbol right here stands for standard state. So this explains to you what conditions that the reaction takes place in. Okay, and for thermochemistry, standard state means 1 atm, so generally open up in the atmosphere. If you have a solution, it's at 1 molar, or 1 mole per 1 liter, and at 25 degrees Celsius, which is room temperature, maybe a little bit warm for room temperature in an air-conditioned room. And then lastly, this RXN right here is just kind of a shorthand for a reaction. It helps me at least keep track of what I'm actually talking about for this. So delta H naught, so change in enthalpy, all energy of a reaction under these conditions. Okay? And so when we use Hess's law, the trick is, or what we do is we use reactions that have known delta H values and we manipulate the reactions. So let me write that down. For Hess's law, we use reactions that have known delta H naught values. Okay, and then we mathematically manipulate them. Okay, so we're going to manipulate the reactions and the delta H values. And so I'll go through and kind of explain how Hess's law works. I'm going to do another video right here where we use enthalpies of formation. So right now I'm just going to focus on Hess's law. So the first that I want to talk about is how to manipulate these reactions for enthalpy at standard states. Okay, and so here's an example of a reaction where you have 2 moles of nitrogen monoxide, and it's a gas, plus oxygen gas. And in this reaction, we we form 2 moles of nitrogen dioxide gas. Okay, and you'll see this 2 different ways. So this reaction has a delta H, so all of the energy when this reaction happens is negative 112 kilojoules. Okay, and this is when that reaction happens at those standard conditions of 1 atm and 25 degrees Celsius. Okay, and remember this little negative sign right here means exothermic. So it's an exothermic reaction, which means energy gets released. So if I perform this reaction at standard conditions, this is how much energy will be released for 2 moles of nitrogen monoxide reacting with 1 mole of oxygen gas, forming 2 moles of nitrogen dioxide. Okay, and then one other thing that I want to show you is sometimes in books the unit on this changes. Okay, and so you'll see delta H equals 112 kilojoules per mole. Okay, that goes back to this equation, and so if you form 2 moles of NO2, it releases 112 kilojoules of heat. Okay, so adding that mole right there kind of allows this to become a conversion. So you can see it, or you'll see it as 112 kilojoules and written after a reaction, or you'll see it written as kilojoules per mole written after a reaction. Those those units kind of mean the same thing when you're talking about when you're talking about energy of a reaction. Okay, so now when we start to manipulate, right, we're going to mathematically manipulate. So if you multiply by a factor, so here what we're going to do is multiply by 2. And so if we multiply all of the coefficients by 2, so 2 times 2 is 4, 1 times 2 is 2, and 2 times 2 is 4, right? I've multiplied all of those coefficients by 2. What I need to do is multiply my delta H value by 2. Which makes sense, right? If I double the amount of reactants that I use in a reaction, it's going to produce twice as much heat. Okay, so if I take 112, multiply it by 2, I get a negative 224 kilojoules of heat. So doubling the reaction is going to double the amount of heat that gets released. In this last step right here, this shows reversing the reaction. So again, I take my initial reaction and I'm going to reverse it. So now the products become reactants and the reactants become products. So here I have 2 moles of nitrogen dioxide gas is going to decompose to form 2 moles of nitrogen monoxide gas and 1 mole of oxygen gas. Okay? When I do that, I change the sign on the delta H value. So up here, maybe I'll go into an orange to match. So up here I had a negative 112 kilojoules or negative 112 kilojoules per mole. But when I reverse that reaction, I change the sign. So now I have a positive 112 kilojoules. Okay? So instead of being an exothermic reaction, this is now an endothermic reaction, which means energy has to be absorbed for that reaction to happen. Okay, and then the very last thing I have down here talks about adding reactions. So if I take and have more than one reaction and I add them together, what I do is I add my delta H values. Okay, so I'm going to walk through just kind of a simple example that's next on how to use Hess's law to manipulate the reactions. So we're going to use Hess's law to determine the delta H naught, so standard conditions, for the reaction right here. N2 gas plus 2 moles of O2 gas forms 2 moles of NO2 gas. Okay, so I was given this information in the problem, or I find it in a table of known reactions. Okay, so when I look at this, I start putting together information that I see in this reaction that I'm trying to find, right? So I'm trying to find a reaction that has N2 in the reactants, O2 in the reactants, and NO2 in the products. So when I'm looking at these reactions, I try and find products and reactants. So first thing, NO is not in my original reaction. That's okay, but N2 is and O2 is, okay? And so when I take this reaction, I want these to become reactants, okay? So what I need to do to make these become reactants is I flip the reaction, okay? And if I flip the reaction, then I change the sign. Okay, so what I'm going to do is take all of these products, and now I'm going to write it in the reactant side. So 1/2 N2 gas plus 1/2 O2 gas goes to NO gas. And now the delta H for this reaction, instead of being a negative 90, is going to equal positive 90. Okay, so first thing, I see my reactants here, or I see them as products, but they need to be reactants, so I flip the reaction. Okay, next step. I look up here and I've got 1 mole of nitrogen, 2 moles of oxygen, forming 2 moles of nitrogen dioxide. Well, when I look at this, I have 1/2 mole of nitrogen, 1/2 mole of oxygen, and 1 mole of this stuff, which isn't even in that original reaction. So let me kind of look down here at this second equation right here. So I found my reactants. Now I need to find my products. And when I look, I have products of NO2, and so here's the product right there, NO2, okay? I have a reactant, but that's okay because that reactant's right there too, and then I have 2 NO gases. So this reaction, I was going to say equation, but this reaction right here, I can actually just leave the exact same. Okay, so I'm going to write it down here as 2 NO gas plus O2 gas goes to 2 NO2 gas. And because I left that reaction the same, I'm going to take this delta H value and keep it exactly the same. Okay, so there's my second step. Now that I've found the reactants and I've found the products, I'm going to double check these 2 reactions. So I'm not using these anymore, like I'm done with those. Now I have 2 new reactions. So here I look and I have 1/2 mole of nitrogen gas, but I need a full mole to match this reaction. Here I have 1/2 mole of oxygen gas, but I need 2 moles. This isn't in my equation. I'm just going to put a little X right there so remember. But look, it shows up as the reactant side over here. So that is actually going to cancel with this part. And I'll show you in a little bit. This right here has oxygen gas. There's 1 mole of that, and I need 2 moles total. And then 2 moles of my product, and I have 2 moles of the product, nitrogen dioxide gas. So what I'm going to do is I need more moles of this nitrogen gas. I need some more oxygen. Since I need 1 mole of nitrogen gas, you see the one right there, what I'm going to do is multiply this by 2. So this top reaction right here, I'm going to multiply by 2. To do that, I have to multiply every single variable or coefficient, and then I also have to multiply my delta H value. So I'm going to take and write this new one down. So 2 times 1/2 is 1 N2 gas plus 2 times 1/2 is 1 O2 gas reacts to form 2 moles of NO gas. And now that delta H value is positive 90 times 2, so 180 kilojoules. Now that I've manipulated this equation, I'm going to go and cross this whole thing out so I don't get confused. Okay, so I've used this top one, I've used these top 3 reactions and I don't need them anymore. So remember, my whole goal, maybe I'll use orange, is to, from this given information, I'm trying to find this equation to find the delta H value. So now I'm going to look at my my reactions, and I have 1 mole of N2. If I look, I have 1 mole and 1 mole, so 2 moles of O2, not just 2 moles, and 2 moles of my product right there. Because I have all the reactants and all the products that I need, what I'm going to do is add these reactions together and hope everything works out. So I'm going to add these reactions together, and if I add those reactions together, then I have to add the delta H values also, okay? So remember, when you're adding reactions, whatever is the same on one side, you write it down, and whatever's the same on both sides, you can cancel it, okay? So I'm going to start up here. I have 2 moles of NO gas. And if you look down here, I have 2 moles of NO gas. Because the number of moles is exactly the same, 2, the compound's exactly the same, NO gas, 2 NO gas, I can cancel those out. So this is going to cancel with that. Okay. Next, I go here and I have 1 mole of oxygen gas, and down here I have 1 mole of oxygen gas. If I add those two together, that gives me 2 moles of oxygen gas. So now I've used this thing and I've used that thing. And then over here I have 1 mole of nitrogen gas. So I'm going to put that down there. Okay? So now I have used every single part of, like every single reactant of those 2 reactions that I'm adding together. Then I draw my reaction arrow. And the only thing that's left on the product side is this up here. So 2 moles of NO2 gas. Okay, so I add those things together, or I've added those 2 reactions together. I've accounted for all of the reactants and all of the products. So the last thing I need to do to find the delta H value is add these 2 delta H values together. So if I take 180 minus 112, or negative 112 plus 180, I get a delta H value of positive 68 kilojoules. Okay, so I've matched my reaction. 1 mole of nitrogen gas plus 2 moles of oxygen gas plus 2 moles of NO2 gas from originally, like what I'm looking for. Adding those 2 values together gives me a delta H value of positive 68 kilojoules. Remember, positive is endothermic. Okay, so endothermic reaction means that it takes energy for this to happen. So again, that was found by taking negative 112 kilojoules and adding it to 180 kilojoules. Okay, so this is how you use Hess's law to determine the delta H for the reaction. If you have any questions, feel free to leave them in the chat.